Okay, good afternoon, all of you. I hope all of you are doing well. So, today's class mainly focus on the actually higher order derivatives. You already learned about so many things in first order equations, differential equations, first order, first degree, and maybe of higher degree. So, we now like to switch over to higher order differential equations. However, instead of confining ourselves to a routine development of the subject, we shall try to look into it with an analytical mind. So, in this chapter, you will learn the linear equations, how you have to deal with the linear equations with constant coefficients. Mostly the second order differential equations with constant coefficients. So, any nth order linear differential equation can be written as dny dxn plus p1 dn minus 1 y dxn minus 1 etc. plus pn minus 1 dy dx plus pn y equal to q, where p1 p2 pn and q are constants or functions of x. It may be constant, may be functions of it, but y is not involved in any of one of these functions. So this is the best example and the standard example of linear equation of nth order differential equation of constant coefficients, or it can be of variable coefficient functions. p1 p2 pn are functions of x, q is also function of x, and no y is involved in these functions. Now in this chapter we'll assume that the coefficients p1 p2 pn are constants. So that is why the name of the chapter is linear equations with constant coefficients. Okay, so we can derive the equations of first order from this equation. How? Let me write n equal to 1 and q equal to 0. Now this q is a function of x. It can be 0, q of x can be taken as 0. Then the equations are called homogeneous. And if qx is not equal to 0, we'll see later how to solve with the equations qx not equal to 0. Then the equations are called non-homogeneous differential equations. Linear homogeneous differential equation, linear non-homogeneous. So qx equal to 0 and qx. So we are considering q equal to 0. We then have a first order linear differential equation dy dx plus p1y equal to 0, and easily you can check e to the power integration p dx integration p1 dx, right, is the integrating factor. E to the power integration p1 dx is the integrating factor. So this is the integrating factor, and you can easily verify that this is the solution of the differential equation. A y equal to a e to the power minus p1x is the solution of this differential equation. This is very important observation. Y equal to a, where a is an arbitrary constant. Okay. Now what about equations of the second order? In that case your n is equal to 2 and q equal to 0, because we are considering q equal to 0, linear homogeneous differential equations. So your equation will be of the type equation 1.2 d2y dx2 plus p1 dy dx plus p2y equal to 0. Right? Now from the previous knowledge that y equal to a e to the power minus px is the solution of this differential equation 1.1, we can suggest that y equal to a e to the power mx may satisfy the above equation. Y equal to a e to the power mx may satisfy the above equation for any value of a. Right? So if you substitute, if you differentiate dy dx equal to the first order derivative of this a m e to the power mx, and if you differentiate twice d2y dx2 equal to a m square e to the power mx, right? Now if you substitute in 1.2, your equation will be look like a e to the power mx into m square plus p1 m plus p2 equal to 0. If you substitute in equation 1.2, this is from the equation 1.2, this is from equation 1.2, right? So an exponential function can never be 0, so you will arrive at this equation only, m square plus p1 m plus ap2 equal to 0, 1.3. So if m is a root of this equation, y equal to a e to the power mx is a solution of the equation 1.2, whatever may be the value of a. This solution is called the trial solution. This solution is called the trial solution. Okay, this solution is called the trial solution. So with this trial solution y equal to a e to the power mx, your second order differential equation reduces to a algebraic equation. This is by algebraic manipulation, substituting the trial solution, you have a quadratic equation, algebraic equation. So differential equation transforms to algebra. So mathematical framework developed our proceedings, as by now we have developed, at least we feel that linear algebra is a natural language to express the salient qualitative properties of differential equations. So we have transformed our differential equation to an algebraic manipulation. This is the algebraic equation, it's a second order. So if we arrive at a second order differential equation, if you are talking about the roots of the equation, there must be different criteria or conditions for roots. Roots can be real and equal, roots can be real and unequal, two roots because this is a quadratic, and roots can be imaginary. So case 1, the auxiliary equation have two distinct real roots alpha and beta. So what is your auxiliary equation? Let me write once again, m square plus p1 m plus p2 equal to 0. That is derived from the differential equation by substituting the trial solution. This is your auxiliary equation, right? This is your auxiliary equation. Now the auxiliary equation have two distinct real roots alpha and beta. Then the general solution of the differential equation is y equal to c1 e to the power alpha x plus c2 e to the power beta x. How this is possible? Let me show you. Let me show you how this is possible. So let me add a page here. Yeah. So if this is the auxiliary equation and the roots are distinct alpha and beta, then this differential equation, that is I am talking about d2y dx2 plus linear second order differential equation with constant coefficient p dy dx plus p2 equal to 0, this differential equation I was talking about, and whose auxiliary equation is given by m square plus p1 m plus p2 equal to 0. This differential equation has two solutions, namely one of the solution is a e to the power alpha x, another solution is y equal to a e to the power beta x, right? Because you have two real and unequal roots alpha and beta, where a and b, oh sorry, you have to take a different arbitrary constant here, A and B are arbitrary constants. Now if you substitute y equal to a e to the power alpha x plus b e to the power beta x in the left hand side of equation, this differential equation in the left hand side of this differential equation, then we have a e to the power alpha x into alpha square plus p1 alpha plus p2 plus b e to the power beta x plus beta square into beta square plus p1 times beta plus p2 equal to 0. Right? If you substitute in this differential equation, now alpha and beta are the roots of this auxiliary equation. Alpha and beta, two distinct roots of this auxiliary equation. So alpha and beta must satisfy this equation. That means alpha square plus p1 alpha plus p2 equal to 0 and beta square plus p1 beta plus p2 equal to 0. Right? So if this is equal to 0, then this expression will be 0. So this is verified that e to the power alpha x plus a e to the power alpha x plus b e to the power beta x is a solution of the differential equation. Okay? Since it contains two independent arbitrary constants a and b, we may regard it as the general solution or complete primitive of the equation, as we are talking about second order differential equation, and we know that second order differential equation has two independent arbitrary constants in the general solution. Okay, so that was the case 1. If you have auxiliary equation has two distinct or real roots alpha and beta, the general solution of the differential equation will be y equal to c1 alpha x e to the power alpha x plus c2 e to the power beta x. Next, let's move to case 2. The auxiliary equation has imaginary roots. That means b square minus 4ac less than 0. The discriminant is less than 0, right? And your auxiliary equation is again given by m square plus p1m plus p2 equal to 0. Okay, this is the auxiliary equation. So imaginary roots, then its general solution is given by this. So let us find out. Let us see in our calculation. So if you have a complex or imaginary roots, then the roots are of the type alpha plus minus I beta. You know that from the theory of equation, imaginary roots always occur in pair, right? If your coefficients are real coefficients of the equation, quadratic, then the general solution is given by, from the previous knowledge, that if the roots are real and distinct, if the roots are distinct, then you can write e to the power alpha x beta e to the power. So in this form we can write, so a e to the power alpha plus I beta, let us consider one of the root as alpha plus I beta x, plus b into e to the power alpha minus I beta into x, right? Now you can write e to the power alpha x into a e to alpha x, e to the power alpha x is a common term, a times e to the power I beta x plus b e to the power minus I beta x, right? Okay, this is the form. Now from Euler formula, actually you know that the second order differential equation first introduced in 1743 by Swiss mathematician Euler. Actually he gave you the concept of this second order differential equation, second order linear differential equation, first introduced by Euler in 1743. He was a Swiss mathematician. Okay, so you know that from Eulerian formula e to the power I beta x we can write it's a complex number form cos beta x plus I sin beta x, right? This is Eulerian form. This is from the complex number. We have the knowledge from the complex number. Plus b into cos beta x minus I sin beta x, right? Okay. E to the power I alpha x is written as e to the power I beta x is cos beta x plus I sin beta x, and e to the power minus I beta x is written as like this. This is your b constant, arbitrary constant. So if you simplify more on that, then you have e to the power alpha x. You can write e to the power alpha x into a plus b cos beta x plus I into a minus b into sin beta x. Okay, now these are the constants a plus b. You can write in a more compact form e to the power alpha x c1 cos beta x plus c2. So I am writing I into a minus b as c2, a plus b as c1. So we can write c1 cos beta x and c2 sin beta x. So this is the form of the differential general solution in the case where the roots are imaginary or complex. Got it? So this is the case, and this is the case too. When the auxiliary equation has imaginary roots, the general solution is given by e to the power alpha x, that is the real parts. Actually your roots are of the type alpha plus minus I beta. So your roots are of the type alpha plus minus I beta. So it can be written as y equal to e to the power alpha x into c1 cos beta x plus c2 sin beta x. Okay, got it? So this is the case 2. Now next we have case 3. When the auxiliary equation has equal roots, that is m1 equal to m2 equal to alpha. So your auxiliary equation is m square plus p1m plus p2 equal to 0, right? So you have a equal roots, then m1 m2 equal to alpha, then the general solution will be like this. So we will look into this also. Let me analyze this. So if your quadratic equation has equal roots, then your discriminant will be 0. So in that case you have p square equal to 4p2, right? P square equal to 4p2. So you have m equal to, the equal roots are given by you look at that, your Sridhar Acharya, if you want to calculate this, the equation, so your equal roots are given by minus p1 plus minus root over b square minus 4ac, the discriminant, minus 4p2 by 2, right? And this part is 0 for equal roots, so it will be minus p1 by 2. So your equal roots are given by minus p1 by 2 and minus p1 by 2. So your differential equation, the given differential equation, the second order linear differential equation, let me write once again, d2y dx2 plus p1 dy dx plus p2y equal to 0, that is given by actually d2y dx2 minus 2m, because your p1 is actually minus 2m from this one, this calculation. So 2m dy dx plus m square y, because your p2 will be m square y, because P2 is given by P1 square by 4, P1 square by 4, right, and P1 square by 4 is nothing but your m square, because you look at that minus P by 2 is m, so you have m square y, and this can be written as d dx of y minus m into y this whole square equal to 0. I am writing d equivalent to d dx. D is a differential operator, so I am introducing a operator d minus m square equal to 0. Okay, so I am using one differential operator. I will discuss more on differential operator later on. So setting a new variable now. So this is your differential equation, second order differential equation transforms to. So setting a new variable u equal to d minus, setting a new variable, okay, u equal to d minus m into y, d minus m into y, m into y, therefore d minus m into u equal to 0. So what I am doing, I am assuming u equal to, setting a new variable u equal to d minus m into y. So ultimately you have a square, so it will transforms to d minus m into u equal to 0. So this is a linear equation, right? This is a linear differential equation. The solution of this differential equation is u equal to c1 e to the power mx. C1 e to the power mx. This is the linear differential equation in u. So you have a u equal to c1 e to the power mx. Now therefore d minus m into y equal to u. So you substitute there, then c1 e to the power mx. This is again a linear differential equation whose integrating factor is, this is the first order linear equation whose integrating factor is e to the power minus mx. So you will see, okay, let me write the integrating factor in this case. Your integrating factor will be e to the power minus mx. This is a first order linear differential, and after solving this you will find the general solution will be y equal to c1 plus c2x e to the power mx. So this is the case when the solution, when the differential equation have two, or the auxiliary equation has two equal roots. So this is the algebraic manipulation, and this is the case when the auxiliary equation has equal roots, that is m1 m2 equal to alpha, then the general solution will be given by y equal to c1 plus c2x into e to the power alpha x. Now let us summarize the concept. So I am introducing a differential operator already, d for d dx and d2 for d2 dx2, d for d dx and d2 for d2 dx2. So this is the differential equation then transforms to d is equivalent to d dx, right? This is the operational substitution. So let us now conclude our topic. Nature of the roots of the auxiliary equation, real and unequal. Your general solution will be y equal to c1 e to the power m1x plus c2 e to the power m2x. Real and equal, then y equal to c1 plus c2x into e to the power alpha x. Conjugate complex alpha plus minus I beta. Then the general solution is given by, the real part will be e to the power alpha x and the complex part will be cos and sine. So c1 cos beta x plus c2 sine beta x. This is from the Eulerian formula, and Euler was the first who introduced the shown the second order differential equation, first introduced the real world with this type of differential equation. So next we'll have some examples on the what we have learned. So first example is d2y dx2 minus 5 dy dx plus 6y equal to 0. Let's solve. Okay, let us find the solution of this differential equation. So before solve, let you have to start like this: y equal to a e to the power mx be the trial solution. You have to write like this: be the trial solution, right? This is the trial solution. So your this equation transforms to auxiliary equation. So let me add a page here so that you can understand very easily. So your differential, the auxiliary equation is, by this substituting this trial solution, the auxiliary equation is so in this case you have a auxiliary equation: m square minus 5m plus 6 equal to 0. M square minus 5m plus 6 is equal to 0. Okay, so m square, so let me write the auxiliary equation is, the auxiliary equation is, after removing those m square minus 5m plus 6 equal to 0. This is the auxiliary equation because a is non-zero arbitrary constant. An exponential function can never be 0. So those parts after taking common it's gone. So you are remain with this algebraic equation, and the roots values of m, that is the roots of this equation, is 3 and 2. So your general solution is given by, the general solution is given by is, the general solution is y equal to c1 e to the power 3x plus c2 e to the power 2x, where c1 and c2 are arbitrary constant. So that is also very easy to solve the problems of second order linear differential equation actually, and from second order we can generate the first order linear differential equations also. Okay, this is how. And so you have to start with the trial solution, you arrive at the auxiliary equation, okay, and then do the algebraic manipulation. The roots are real and distinct, so you have the general solution this, and you have to write c1 c2 are arbitrary constant. Next, example 2, solve d2y dx2 plus 4 dy dx plus 4y equal to 0. So again your trial solution is y equal to a e to the power mx be the trial solution. So your auxiliary equation is m square, actually you have a e to the power mx into m square plus 4m plus 4 equal to 0, because this is a non-zero quantities a and e to the power mx. So you are arrive at the auxiliary equation m square plus 4m plus 4 equal to 0. So let me write here, we have a space here, this is example 2. So this is nothing but your m plus 2 equal to 0. This is your auxiliary whole square equal to 0. This is your auxiliary equation. Okay, so your solutions are m equal to minus 2 and minus 2, right? So roots are real and equal. So the general solution is, you can write the general solution. So the general solution is y equal to c1 plus c2x into e to the power minus 2 x. Okay, where c1 c2 are arbitrary constants. This is the way of writing. Next, let's have a complex. So this is the equation, it's auxiliary equation, again y equal to a e to the power mx be the trial solution, and your auxiliary equation is m square minus 2m plus 2 equal to 0. Let's search for the solution. So you have a complex part, so minus b plus minus b square minus 4ac, b square 4 minus 4ac is 8 by 2a. So you have 1 plus minus I, right? I is the iota, root over minus 1. So you have a complex roots or imaginary roots. So your general solution is given by, your general solution in this case is given by y equal to e to the power x, 1x, because your real part is 1. So x into c1 cos beta x, c1 your alpha is 1 and beta is 1, right? Because alpha plus minus I beta, so you have a e to the power x c1 cos beta x, so cos x plus c2 sin x. So this is the general solution of the given differential equation. Okay, clear? So clear everybody, this is how you have to deal with the problems. It's very easy to deal with the problem. Just you have to identify the auxiliary equation and the cases, whether the equation, algebraic equation, has real distinct roots, equal roots, or imaginary roots. Now let me move to the little bit higher order, more than 2. Let me talk about more. Yeah, higher order, higher than the second order. So this is the nth order. So if auxiliary equation will be look like this, if y equal to mx be y equal to e to the power mx be the trial solution, then your auxiliary equation will be m to the power n plus p1 m to the power n minus 1 plus pn minus 1 m plus pn equal to 0. So this is the auxiliary mth degree equation, nth degree equation, algebraic equation. It must have n roots. So if all have the n distinct real roots, rule 1. So you can generalize your concept of second order for n distinct real roots. You have c1 e to the power m1x, c2 e to the power m2x plus cn e to the power mnx, right? So you have n distinct real roots, then you can generalize your concept of the second order. So if you learn the second order, that is enough for you, because you can generalize the second order concept of the differential equation. Rule 2, actually higher order algebraic equations are reducible to second order. So that is the concept of the if you know second order differential equation very well, then you can generalize your concept. Rule 3, m1 m2 m3 are each equal to m, all are equal, then the corresponding part, actually you have a nth degree equation, so maybe there are some more equations involved, more roots involved. So corresponding part of the general solution will be c1 plus c2x plus c3 x square e to the power mx, right? And you have a pair of imaginary roots, then your corresponding part of the general solution will be this, you already know. But you have a pair of imaginary roots occur twice. That means 2 pair of imaginary roots. That means alpha plus minus I beta. Again you have a alpha plus minus I beta, 4 roots. And the other roots may be real, maybe m1, m2, etc. Then the corresponding part, I am just talking about a part of the mth degree equation. So e to the power alpha x, c1 plus c2x cos beta x plus c3 plus c4x. Look at that, you have a 4 arbitrary constants, because you are talking about a 4 roots. So you have a 4 arbitrary constants. So number of independent arbitrary constants equal to the order of the differential equation, right? Okay. So let's have a example. It's a cubic equation. Let's solve this. The auxiliary equation I'm writing in a short. So you will check for the trial solution, and y equal to e to the power mx will give you the auxiliary equation. The auxiliary equation is given by m cube minus 3 m square plus 4 equal to 0, right? And if you solve this, you will get m plus 1 factor, m minus 2 and m minus 2 equal to 0, right? So what is the general solution of this? You have 2 equal roots and 1 different root. So your general solution will be, let me write the general solution, y equal to c1 plus c2x. You have 2 equal roots, so that is why I have taken 2 arbitrary constant inside the bracket, e to the power minus 2x plus c3 e to the power minus x, because you have a distinct root minus 1. So this is how you can deal with the concept of the second order linear equations, and your higher order differential equations can be generalized, the solution can be generalized with the concept of the second order linear differential equation. So most important part of your differential equation is the second order linear differential equation with constant coefficient. So if you learn the second order differential equation, that would be enough for your life, because that will generalize, you can generalize the concept in the higher order differential equation. So that's all for today, all of you. So thank you all of you for your patience. Just follow my lectures in the next couple of days, and follow my videos, my YouTube channel. Thank you all of you for your cooperation.